Hello everyone, and welcome to this video on using the fundamental theorem of linear algebra to find the general solution to a system of linear equations. So in this video, I'm going to start off by stating the fundamental theorem of linear algebra, and I'm not going to prove it. I'm not going to write a proof out for it. That's not the point of this video. Just going to make the statement and look at some consequences of that statement, and then go into some examples where we're given a system of equations expressed as a matrix equation, and use the fundamental theorem to express the solutions to that system if it has any. And I've picked some examples where the systems actually do have solutions. We'll express those solutions as in a particular way that we'll see coming up. Alright. So what is the fundamental theorem of linear algebra? So it states that for any m by n matrix A, and this is implied to be with real number entries, okay, real number entries in matrix A. So for any m by n matrix A with real number entries, the following statements are true. And really the most important one is this first one, because I'll show you in a second how the second statement really just comes from the first statement. The row space of A and the null space of A are orthogonal complements. So a way to say that symbolically, right, row of A, the row space of A, equals, the null space of A complement. Right? Remember this symbol, this orthogonal symbol here, is the orthogonal complement of the null space of A. And vice versa, you could say that the null space of A was the orthogonal complement of the row space of A. Right? Another way to state this, remember the row space of A was the same as the column space of A transpose. So I could have also written this as the column space of A transpose equals the null space of A complement, right? The orthogonal complement of the null space of A. And I'm assuming here that you remember what these are. Right? Remember, just real quickly, the row space of a matrix was the subspace spanned by the rows of the matrix. Simple as that. And the null space of a matrix was the space of solutions to the equation A times some vector x equals the 0 vector. Right? It was the set of all solutions, the space of all solutions to that homogeneous equation. So this is a nice result. I mean, this is huge, telling us that any vector from the row space of a matrix will be orthogonal to any vector in the null space, and vice versa. And of course, I'm going to assume we'll be doing the dot product here for our inner product. Remember, the concept of orthogonality depends on the inner product. We're going to define the inner product as the dot product throughout this video. In fact, I will write this off to the side. The inner product that I'm using here today is the dot product. Just remember, you have to pay attention though. Like, sometimes the inner product may be defined in some other way, but we're gonna make it nice and easy for ourselves today. And it's called the standard inner product. It is the one that's most often used anyway. All right, so that's fine. All right, so the row space of a matrix and its null space are orthogonal complements. And that really kind of leads me into the second statement as well, where the column space of a matrix and that left null space of the same matrix are also orthogonal complements. Alright, so symbolically the column space of A is equal to remember the left null space of A was just the null space of A transpose. So the column space of A is the null space of A transpose's orthogonal complement. Right. But remember, the column space of a matrix is just the row space of the transpose. So another way I could have written this, and you see how this is exactly the same statement here as in statement 1. The row space of A transpose is the orthogonal complement of the null space of A transpose, and that's saying exactly the same thing as the first statement. The row space of a matrix and the null space of that same matrix are going to be orthogonal complements, right? Every vector in one space will be orthogonal to every vector in the other space. Okay. All right, so now that we have these orthogonal complements out, some consequences of this. Now remember, if your matrix is an m by n matrix, the row space will be a subspace of Rn. The null space will also be a subspace of Rn. And if there are orthogonal complements, if you recall, an inner product space can be expressed as a direct sum of a subspace and its orthogonal complement. So that's what I have written here. So one consequence of this theorem is that any Euclidean space, Rn, can be written as the row space of an m by n matrix plus, in a direct sum, or the plus sign with the circle around it, the null space of that same matrix. Right? Again, where A is an m by n matrix with real entries here. So remember what this means when I say that Rn is a direct sum of the row space and null space of some m by n matrix. This means I can take any vector from Rn, any vector, and express it as a sum of a vector from the row space of A plus a vector from the null space of A. And I should be able to do that in a unique way as well. Right? That happened with direct sums. Well, if I can take any vector from Rn and express it as a sum of a vector from the row space plus a vector from the null space of a matrix, that leads me to the following statement. Right? A consequence of this is that any solution to a system of equations, now this is written as a matrix equation here, so some m by n matrix A times some n by 1 vector x, right? This x is a vector in Rn, right? X would belong to Rn, right? Have n components. So an m by n matrix A times some vector from Rn will be equal to another vector from Rn, right? B would also belong to Rn. But our solutions are, the vectors I can replace x with, right? So a consequence of this direct sum statement is that any solution to Ax equals B, if it has solutions, because if it doesn't have solutions, then there's no point in this. But any solution to Ax equals B can be decomposed in the following way, right? Remember the orthogonal decomposition in my last video. I can take any solution x and express it as a vector from the row space, right? So this is x sub r for row space, plus a vector from the null space of A, x sub n. Okay, and I should be able to do this, in a unique way for any solution. All right, so let's do this, right? Let's take a system of equations and express our solutions as a row space vector plus a null space vector, right? The sum of two orthogonal vectors. because remember, row space and null space should be orthogonal complements. Alright, so my first example, and I've chosen examples that'll actually have solutions, right, where the system will be consistent. Because if there is no solution, then there's no point to this. Right? There's nothing to do. All right. So my matrix. So for example, my first example here has a 3x2 matrix A. Right. A is a 3x2 matrix with rows 1, -4, 3, -2, -2, 8. And the B, the column on the other side of the equation is the vector 17, 51, -34. So, so A times X equals B looks like this. We have the matrix 1, 3, -2, -4, -12, 8. Now this is a 3x2, so I need to multiply it by a 2x1 to get this 3x1 over here. Now, so the vector X will have two components, it'll be from R2, say X1 and X2. Right. So the vector X is from R2 equals, and the 3x2 times the 2x1 equals this 3x1. So here's the AX equals B. Right. And remember how, what I'm going to do here is solve it the way I've normally solved it. The way I would normally solve a system of equations. I'll set up an augmented matrix. Right, so here's the augmented matrix for this system. Coefficients of x1 down the first column, or these would be the coefficients of x2 down the second column. All right, then a little bar where the equal sign would go, and then the column B over there, 17, 51, and -34. And then I would take this and put it into reduced echelon form or reduced row echelon form, RREF. Now this one's pretty simple. I don't need to go to a calculator for this one. See how the first row, if I just multiplied that by -3 and added it to the second row would be full of zeros. And if I take the first row, multiply it by 2, and add it to the third row will be full of zeros. Okay, so my reduced echelon form is simply the first row is 1, -4, 17. And the next two rows are just full of zeros. And this, and my pivot here, the leading 1, the leading non-zero entry in this first row is a 1. You got zeros below it. This is in reduced echelon form. Alright, and then one that, hopefully this is all familiar to you by now. If you're at this video by this point, you've probably seen this. So then I set up my free variables and basic variables or leading variables. So there's a pivot, the leading 1 in this first column, which corresponded to the coefficients of x1, right? So x1 is basic, or a leading variable, and then x2 is a free variable. And as I like to do with all my free variables, I like to assign some other parameter to them. So I'm going to let x2 be replaced by, say, t, where t is just any real number. Alright, and then from the first, the only equation here that means anything, the second equation and third equation are simply 0 equals 0, which is fine, right? That's a true statement. This first equation here is telling me that x1 minus 4x2, so minus 4t, will be equal to 17. So the value of x1 is 17 plus 4t. Alright, and then I'll express the general solution on the next page. So the general solution, the description of all the solutions of this system here, what can I replace x1 and x2 with, is the following. I can replace this vector x, this this x1, x2, with x1 is 17 plus 4t, and then x2 is just simply t. And what we're going to do is I'm going to break this up. All right, I've got terms without a variable, and then remember how you separate the free variables. I got terms without the free variable and terms with the free variable. I can break this up into this sum. 17, 0, right? The vector 17, 0 plus, and then the terms with, these both have t in it. I can pull t out times the vector 4, 1. All right, if you recall from a video a while back, it's been a while, this 17, 0, this is a particular solution to the system. Usually called like XP, right? All right, and then all the terms with free variables attached represented the solution to the corresponding homogeneous equation. Right? This t times 4, 1, this represented solutions to the corresponding homogeneous system which was a times x, equals the 0 vector. And that means that these make up the null space. Right? And in an earlier video, this was represented by vector x sub h for homogeneous, right? And this was x sub p for particular. But these solutions to the homogeneous system, this is the null space of A. Right, so I've got that down. I'll write that over here. So the null space of A, the null space of our matrix, is just any scalar multiple of the vector 4, 1. Right? So the span of the set with the vector 4, 1. And what I want to show you now too is the row space of A. Now the row space of A is easy to I've already put matrix A into reduced echelon form. That was up here. Right, here was matrix A in the augmented matrix. Right, and then here with the 1, -4, 0, 0, 0, 0, that's A prime, right? That's A in reduced echelon form. So if you remember, in reduced echelon form, the pivot rows, the rows with those leading ones, made up a basis for the row space of the original matrix. Right? So the row 1, -4. Now I'm going to write it as a column, just to maybe save a little space. But we see here from the reduced echelon form of A, right here, that the row space of A is the span of the set with the vector 1, -4. And again, I'm writing it as a column. Just maybe I could put transpose here just so you know that it's actually a row vector. But still, 4, 1, 1, -4. And look at these basis vectors. Look at these basis vectors. if you take the dot product of 4, 1 with 1, negative 4, you're getting 4 times 1 plus 1 times negative 4, 4 plus negative 4, that's 0. These are orthogonal. So these are orthogonal subspaces. And they point in two different directions, so we get a base. These two vectors, 4, 1 and 1, negative 4, do form a basis for R2. Right? So R2 is a direct sum of the row space of A with the null space of A, as I mentioned earlier on an earlier page. Let's take a look at pictures of these. Right, let's take a look at pictures of these, and then we're going to express our solutions as a row space vector plus a null space vector. Right. So I'm going to go to the GeoGebra website here. Now, let me put up. This is the 2D version. Right, here's the origin. Little dot there, and then remember the null space was the span of the vector 4, 1. Right, so here's the vector 4, 1. The span of that vector, remember, would be a line, right, all containing all scalar multiples. A line with all the scalar multiples of this vector. This line that just appeared, that's the null space of A, the null space of my matrix. All right, and maybe I'll color these a bit. Right. So the vector red and the space green, how about that? Okay. All right, so again, this green line is the null space of the matrix. And then we saw, after looking at A put into reduced echelon form, the row space of A was the span of the vector 1, negative 4. All right, so here's the vector 1, negative 4. And you see that there. Now, again, the dot product is my inner product, all right? You can see pretty much from here that those two vectors, right, the vector 4, 1 and 1, negative 4, form a 90-degree angle at the origin there. They are orthogonal under the dot product. But then let me put in the, what was the row space, right? The row space was the span of this vector, right, which would be a line containing all scalar multiples of the vector 1, negative 4. And there it is in black. But you can see that these are orthogonal subspaces, right? They do form a 90-degree angle. They're orthogonal under the dot product. And so any vector from the null space with any vector from the row space in black will be orthogonal. And they point in two different directions, so they, these two vectors, 4, 1 and 1, negative 4, right? These do form a basis for R2, so you could also say R2 is, again, the direct sum of the row space of A with the null space of A. All right, now, as I mentioned on an earlier page, remember I said that we could express, right? That means we should be able to express any solution as a vector from the row space plus a vector from the null space, right? I wrote that here, right? And I'll write it again. I'll write it again here. Right? So we should be able to express, we will be able to express any solution to ax plus b, or sorry, ax equals b, as the following, right? Where I can rewrite my solution x as a vector from the row space plus a vector from the null space. That was that x sub r plus x sub n. Okay. All right. Now, let's do that. All right. So I'm going to do that here with my particular solution? Because look at this particular solution. You might think, hey, 17, 0. Is that in the row space? Because here I have a row space vector plus some. This would be any null space vector, right? Any multiple of 4, 1 is in the null space. So you might be asking yourself, is this 17, 0 in the row space? Well, clearly not, right? Is 17, 0 a multiple of 1, negative 4? And even looking back on the website, right, if I put in the vector 17, 0, clearly, and I'll make this a different color. There it is there. It's pointing off to the right there. It's way off, 17, 0. There it is. The row space is this black line, right? The span of 1, negative 4. Clearly this vector 17, 0 is not in the row space. So I don't have my solutions set up the way I would like, right? Using the fact that R2 is a direct sum of the row space and column space. But I should be able to take 17, 0 and express it this way, right? So we see that, so for example, right, x equals 17, 0. Right, that is a solution, as we saw earlier, right? My particular solution here, 17, 0. 17, 0 is a solution, but it doesn't belong. Right, 17, 0 does not belong, a little slash through that, the row space of A, and it also doesn't belong to the null space, right? You saw that as well. It doesn't belong to the null space. Right, so this right now, right, this solution right now is not in this form. I would like to put it in this form. Okay, so how do we do that? Well, that's going to involve, I did this in my last video. I remember the last video talked about orthogonal projections onto subspaces, and how do I write the orthogonal projection of a vector onto a subspace and then write its orthogonal decomposition? Well, that's exactly what I'm going to do here. Okay. So let's do that. So first thing I want to do is I'm going to project this vector onto either the row space or the null space. Okay, whichever one I think is least complicated. Now, they're both spaces are dimension 1, so it doesn't matter, right? You're going to see that here in a second. In fact, I'll show you. I'll do it both ways. But I'll first project. I'm going to project 17, 0 onto either the row space of A or the null space of A. All right, whichever has the smaller dimension. All right, but they both have the same dimension. So I'll say whichever one has the smaller dimension. That would be the easier one to project onto, because you have to do sum of fewer terms. All right. Well, like I said, they're both the same dimension. The first space I found was the null space, so I'll do the null space. All right. So how about onto the null space? Let's project onto the null space of A. All right. So if I'm going to do that, remember, hopefully you've been watching, following. Remember from the last video, it means if I'm going to project onto a subspace, if I'm going to project a vector onto a subspace, I need to find an orthogonal basis for that subspace. Right, so find an orthogonal basis. That's the key word, orthogonal. Now, when there's, it's only dimension 1. Right, here's a basis for the null space of A is this set with the vector 4, 1 in it. That's only got one vector. So we could say, say that it's an orthogonal basis. Right? Remember, an orthogonal set meant every pair of vectors was orthogonal. There aren't any pairs of vectors in here, so we could say vacuously that this is an orthogonal basis. Right? So this is okay. Right? This set with the vector 4, 1. All right, so I'm going to call this vector 4, 1 here. I'll call this vector u1. And remember the projection vector, which if I'm projecting onto the null space, that's going to be that xn. Right? So xn, remember I said I had xr plus xn. We're projecting onto the null space. I'm getting xn is going to be the sum of the projections of 17, 0 onto every vector in the orthogonal basis. Well, there's only one vector here. Alright, so that's going to be the projection of my vector x, right, of 17, 0 onto u1. Right. Remember the little formula for this? That was the inner product of x with u1 divided by the inner product of u1 with itself times u1. Alright. Well, inner product here is the dot product. So in the numerator of the scalar, what's the dot product of 17, 0 and 4, 1? That'd be 17 times 4 plus 0 times 1. That'd be 68. All right, 68 plus 0. So 68 in the numerator. And then the inner product of u1 with itself, right, this 4, 1 with itself, that'd be 16 plus 1, that's 17. Which we can see here, that's just 4. Right, that's just the number 4. Right, we already saw 4 times 17 is 68. So 68 times u1 is 4, 1. So this is the vector 16, 4. Right, there's the projection of 17, 0 onto the null space. Let's take a look at that. Go back to the website here. I'm going to put in the vector 16, 4. So you see that that's on the null space, right? This vector that just popped up. This is 16, 4. And the end of that vector should be the closest distance to the vector 17, 0 that's on the null space. All right. So again, if I were to draw a little, from the end of 17, 0, draw a little perpendicular segment to the null space, I'd get the end of this vector here, this 16, 4. That's the projection vector. So it looks pretty good. All right. Alright, now I could do the same thing for the row space to find xr. Alright, I could do the same thing for the row space to find xr. I could project 17, 0 onto the row space as well. But I think an easier way to do it is just a little subtraction. Alright, because remember, we're trying to write this. We're trying to write our solution 17, 0 as some vector from the row space plus some vector from the null space, and I have the vector from the null space and I have the vector x, right? This was 17, 0 equals this vector from the row space plus and then 16, 4. Right, and then I subtract 16, 4 and we'd get our vector from the row space, right? So it's just a simple matter of subtraction. So what's 17, 0 minus 16, 4? That'd be 1, negative 4, the vector 1, negative 4. All right. So there we have it. All right. So our solution is, our 17, 0. I can break this up to a vector from the row space, right? 1, negative 4, plus a vector from the column space. I'm sorry, not the column space, the null space. All right, that was 16, 4. And let's see if that works out. Right? And these are two orthogonal vectors, right? Take 1, negative 4 and 16, 4, do their dot product, you're getting 0. You're getting 16 minus 16. Right, so back on the page here, let me put in the vector 1, negative 4. Well, it's already there. Right, that's v2. And do you see that if I moved v2, oops. All right, let me just clear this stuff out. Right? Right, so here's again vector 1, negative 4. I already had it, but I lost it. So vector 1, negative 4. Right? You see that's orthogonal to 16, 4, and if I put them together, I move this vector over here to the end of v4. You can see that they add to make the blue vector. Right? So this blue vector was 17, 0, right? One of the solutions to my equation, and it's broken down to its orthogonal components. Right? It's being orthogonally decomposed to a vector from the null space plus a vector from the row space, right? And those are orthogonal, the sum of two orthogonal vectors, 16, 4, and 1, negative 4. Beautiful. All right, so now we can use this idea to express the general solution to my equation, right? So if you go back up to the general solution, right, that looked like this. It was 17, 0 plus some multiple of the vector 4, 1. Remember, I can rewrite 17, 0 as 1, negative 4 plus 16, 4. Right, so I'm going to do that. So going back to the general solution, we can now write this way. Right? So now the general solution of this system is looking like this. X equals 17, 0 is 1, negative 4. Right, there's a vector from the row space, plus 16, 4, which is just 4 times 4, 1. Right, 4 times 4, 1, and then plus, that's 17, 0, plus some multiple t times 4, 1. And putting these together, we get x equals, 1, negative 4, plus, and then, both, see how both of these have the vector 4, 1 in common? So I could factor that out, the vector 4, 1 pulled out, and then, 4 plus t is just some number, right? Remember, t can be any real number I want. So 4 plus t can be any real number I want. I'm going to call that s, right, where s equals 4 plus t, right? Or s can be any real number you wish, right? You just let t be anything you want, right? If you let t be 100, s is 104, right? So s is any multiple, any real number, any scalar. And there you go. Right, here's a description of the general solution to my system. Right, a description of the general solution to my system. where I have a vector from the row space plus, some vector from the null space. Right? 1, -4 is obviously in the row space, plus, and then any multiple of the vector 4, 1 was in the null space. Right? Right, and you can test this out, right? Find some other solutions. Whatever you like. One thing I want to point out is that this vector from the row space is the only vector from the row space that gives you solutions. Right. Let me show you. Right. So XR, right, the 1, -4, this is the only vector from the row space of A that will be a solution. That is a solution of A times X equals B. Because look, if I replace X with, XR, this is A times, remember I can replace X with XR plus XN, right? And then we distribute, this is A times XR plus A times XN. And remember, XN is a vector from the null space. So A times XN is always going to be the 0 vector. Right? So we have A times XR must be equal to B. Right? And it can't be some other, because this is the 0 vector all the time. Right? And it can't be some other vector. Right? Because remember, another vector from the row space would be a multiple of XR. Another vector from the row space would be, say C times XR, so where C is a scalar. Well, A times CXR would be C times A times XR would be the scalar times B, not B itself, right? So if the say the scalar is not 1, right? If I'm talking about another vector. So if C is not 1, you're not getting B back. So there's only going to be the one vector from the row space that actually satisfies the equation. Right. Okay. There are going to be lots of vectors from the null space because, like I said, you can add, take the vector from the row space, this XR. I can add any multiple of 4, 1 and get a solution. Right. Right. Okay, so let's do that again. So my next example, same setup, right? I'm given a matrix A and a vector B, and we're trying to find solutions to this equation, right? A times X equals B, and again, I'll write it out. So it's going to be, the matrix A, 1, 1, 3, first column, 1, 0, 2, second column, -1, 1, -1, third column, and the vector X would have to be a 3 by 1, right? This is a 3 by 3 matrix now. So the vector has to have 3 components, x1, x2, and x3. Equals, and then the B over here, the -1, 3, 1. Alright, so as before, I'm going to find the general solution first, All right, I'm going to find the general solution first, and that'll be written as some particular solution plus the solutions of the corresponding homogeneous, right, the xp plus xh. And then we're going to take that particular solution and write it as a vector from the row space plus a vector from the null space of A, just like I did with the last example. All right, so I start off with my augmented matrix, or matrix A is on the left here. And then a little bar for the equal sign, then vector B on the right. All right, and put this into reduced echelon form, which this time I'll actually go to a calculator. I mean, you can do it with Gaussian elimination, Gauss-Jordan elimination by hand, but I'm just going to save a little time. All right, so in the my 84 plus here, go to the matrix menu, over to edit. This is a this augmented matrix is a 3 by 4. All right, then put in the entries. -2, -1, 1. Alright, then get out of here, go back to the matrix, over to math, RREF, right? RREF, and then matrix A that I put in. Alright, so here we're getting this. So 1, 0, 0 for the first column, 0, 1, 0 for the second column, 1, -2, 0 for the third column, little bar, and 3, -4, 0. Okay. So again, nice thing happening here, 0 equals 0 at the bottom. You can ignore that. That is a true statement. Look for my pivots. All right, the pivots, those leading ones are in this column and this column. Those leading ones in each of those rows, the pivots. And remember that corresponds to the first column corresponds to x1, so x1, and the second column corresponds to x2. x1 and x2 are my basic or leading variables. And then x3 is free. Right. So again, only one free variable, right? So that means the null space is going to have a dimension of 1 again. So I'm going to let x3 be replaced by t, where t is real, right? Any real number. All right, and then from the first row, we would see that x1 would be equal to 3 minus t. Right? You have 3 on the other side, and you have x1 plus t equals 3, subtract t. Second row, we have 1 at x2 would be equal to -4, right? I got -4 on the other side, and then plus 2t. Right? Plus 2x3 or plus 2t. Alright, so then I can describe the general solution. Right. So the general solution to this system, this equation, is I can replace x with any vector that looks like the following. The first component is 3 minus some choice of t. The second component is -4 plus 2 times my choice of t, and x3 is just my choice of t. And then as I did with the last example, I'm going to split this up, split up terms without the free variables and terms with the free variables. So one vector, without the free variables is 3, -4, 0. Plus, and then all the stuff with the free variables, those all have just t in it, pull t out, times the vector -1, 2, 1. Alright, so like before, this is a particular solution to the system. then this T times -1, 2, 1, this describes the null space. These are all the vectors in the null space. These are the solutions to the corresponding homogeneous equation, AX equals 0. All right, so I'm saying here that the null space of A is simply the span of, again, a single vector. It has just a dimension of 1. The span of the set with the vector -1, 2, 1. We're also seeing the row space, just like last time. All right, the row space of A is the span of 1, 0, 1 and 0, 1, -2. Because there's matrix A put into reduced echelon form, and those pivot rows do form a basis for the row space of A. All right, so the row space of A is the span of the vectors 1, and again I'm writing, I know they're rows, but I'm writing them as columns. Right? 1, 0, 1. If you want to put a little transpose there, that's fine, just to let you know it's a row vector instead. But they have the same components, right? It doesn't matter if I write them as a row or a column. And then 0, 1, -2. Right, that was the first row, the second row of my reduced row echelon form. And look, these two spaces are orthogonal subspaces. Take the dot product of -1, 2, 1 and 1, 0, 1. You get 0. Take the dot product of -1, 2, 1 and 0, 1, -2. You get 0. All right, so the basis each possible pair of basis vectors have a dot product of 0, have an inner product of 0. So these are orthogonal subspaces, and these are vectors that, if you put all three together, would form a basis for R3. So these are orthogonal complements in R3, right? So R3 is the direct sum of this row space and this null space. And that should always happen. Okay, that means, right, remember again, this means that I can take any solution, I can take any of these, any solution, and write it as a vector from the row space plus a vector from the null space. Right, and again, when you find that vector from the row space, that will be unique. All right, well, let's do that. So just like last time, right, look at my general solution here. All these vectors, right, are from the null space. So, if this vector is from the row space, that would be wonderful. Right, that would be fantastic, because then I'd be done, and I'd have my general solution written as a row space vector plus null space vector. But let's take a look at this solution, right? All right, so let's express solution x equals 3, -4, 0. Let's express this as some vector from the row space plus some vector from the null space, xr plus xn. All right, so remember that means I'm going to do the orthogonal decomposition of 3, -4, 0. I will project 3, -4, 0 onto either the row space or the null space. Now, I'm not going to do the row space because it has a higher dimension. You can. It's just, remember, you have to project onto a subspace. You need to find an orthogonal basis. And this is not an orthogonal these two vectors here do not make an orthogonal basis. Their dot product is not 0. It's -2. So then I'd have to use Graham-Schmidt, to construct an orthogonal basis from this. So it's easier to work with the null space here, project onto the null space, because it has a smaller dimension, and its basis only has one vector. So I can I can say that this is an orthogonal basis. All right, so let's do that. I'm going to project onto the null space first. All right, so remember the projection, that was this xn, right? This is the projection of x onto the null space. Well, there's only one vector in this basis, right? There's only one vector in the basis for the null space. So it's projecting 3, -4, 0 onto the vector -1, 2, 1. So remember the numerator would be the dot product, right? So -3 plus -8 plus 0, that'd be -11 for the numerator. Then I'm projecting, then I do -1, 2, 1 with itself, right? The dot product of -1, 2, 1 with itself. So that'd be 1 plus 4 plus 1, be 6. And then times that vector -1, 2, 1, right? The vector you're projecting onto. Okay, there we go. This is a vector from the null space, right? It is a scalar multiple of -1, 2, 1. And it should be, it is the projection of 3, -4, 0 onto that. Now let me actually bring up some pictures. Right? I haven't shown you any pictures here. All right. So back to the website. Now this, I'm going to go to the 3D calculator. So remember the red axis, green axis, and blue axis, the directions that we're going in here. So here's here's the origin, 0, 0, 0. Dot showed up. Now the null space, right, remember I said the null space of our matrix was the span of the vector -1, 2, 1. All right, so there's -1, 2, 1. You can barely see it, but it's -1 in the red direction, 2 in the green direction, and then 1 in the blue direction. Oops, sorry about that. I am shifting the wrong screen. All right. Yeah, so you can see that here, hopefully. All right, there's -1, 2, 1 in black. Go back to the home view. Okay, and then the span. Right, the span of that vector is just a line. Right, so here's the null space. All right, and I'll maybe color these in a bit. Right, so that green line on the screen is the null space of A, right? The span of the vector -1, 2, 1. All right, then my row space. Remember the row space I had written up was the span of 1, 0, 1 and 0, 1, -2. So here's 1, 0, 1. And the vector 0, 1, -2. All right. So there's those two. Now they look like they're pointing in the same direction, but they're not, right? You can clearly, if I move it around a bit, you can see they're pointing in different directions, those two. Maybe go back to the main view. All right. So you see the red vector, these two black vectors, pointing in 3 different directions, right? Form a basis for our 3. And then let me put up the span of those 2 vectors. Remember, the span of 2 vectors was a plane. Okay, this plane here, right? You see those 2 black vectors are forming, they're spanning this sheet, this blue sheet on the screen. Okay. And you see that these are orthogonal, right? Then you see the green line and the blue sheet, form a 90-degree angle where they meet. See, maybe you can see it there. But yeah, the null space is the green line. The blue plane, the blue sheet, is the row space. All right, and then we just said that our solution, remember that particular solution that we're looking at is the vector 3, negative 4, 0. So let me put that up and show you that that's not in the row space or the null space, right? If I put in the vector 3, negative 4, 0, see this new black thing showed up on the xy plane. See that that's not on the blue sheet or on the green line, right? But we can express it as the sum of a vector on the blue sheet with a vector on the green line, right? The row space and the null space. Now we found our null space component, right? The null space projection, the projection of that vector, the vector 3, negative 4, 0 onto the null space was negative 11/6 times the vector negative 1, 2, 1. All right, and there it is there. All right, you see this black tip that just showed up. So there it is, negative 11/6 times the vector negative 1, 2, 1. It's on the green line, it's on the null space, and it is the closest vector to the vector 3, negative 4, 0. This distance that I'm pointing out right here. That's the shortest distance from the end of vector 3, negative 4, 0 to the green line. All right, so we have our projection vector. Now I would like the projection onto the null space. Now I would like the projection onto the row space. Right. So I go back. Now I already have xn, and let me actually multiply this out. Right. So the x sub n here, the vector, the projection of 3, negative 4, 0 onto the null space is positive 11/6, negative 11/3, and negative 11/6. Right. All right. And now I want to find that vector from the row space. All right. So remember that x, I'm going to break up into xr plus xn. I already got it up here. So we have xr is going to be my vector x, the 3, negative 4, 0, minus the xn, which is this 11/6, negative 11/3, negative 11/6. And putting these together, right, getting common denominators and all that, right, this is 18/6 minus 11/6, so that's 7/6 for the first component. Then this is negative 12/3 minus negative 11/3 would be plus 11/3. So negative 12/3 plus 11/3 would be negative 1/3. And 0 minus negative 11/6 would be plus 11/6. All right. Okay, and let me put this vector in. Right. Let me put this vector in on the website, and then I'll erase some other stuff, but hopefully show more clearly that this is the orthogonal decomposition of 3, negative 4, 0. Right, so v6 here I've got is the vector, this is this xr 7/6, negative 1/3, and 11/6. All right, now let me get rid of some of these. Now hopefully you see. I'll keep the null space and row space up. All right, so you see the vector I just entered was that r, right? You see that 7/6, negative 1/3, and 11/6. See that vector is on the blue sheet. Right, you see it there. It is in the row space. And the vector, negative 11/6 times the vector negative 1, 2, 1, that's on the null space on the green line. And their sum, right, the sum of these two orthogonal vectors should be the vector 3, negative 4, 0. Let me show you that here. That says, I'll just do v5 plus v6. Those are v5 plus v6. See how it's the vector 3, negative 4, 0, right? So the sum of these two vectors, the one from x, the xn and the xr, the one from the null space and the row space, gives me that particular solution of 3, negative 4, 0. All right. Wonderful. So I'm going to write that. Right, so we have 3, so our particular solution, right, 3, negative 4, 0, this was a solution to the equation, can be expressed as, 11 sixths, negative 11 thirds, and negative 11 sixths, plus this 7 sixths, negative 1 third, and 11 sixths. All right, and this is a vector from the null space, and you can switch the order if you want, but this is that xn, right, a vector from the null space, and here was a vector from the row space, that xr. All right, and then I'm going to use this to rewrite the general solution. All right, so going back to the general solution. So I'm going to rewrite 3, negative 4, 0 using this, and I'll switch the order. All right, so I have it the way I had originally with the xr plus xn. Sorry about that. So back to the general solution. We have x equals, so again down here, instead of 3, negative 4, 0, I'm going to write that as the vector from the row space. All right, the vector from the row space, that was its projection onto the row space, that'd be that 7 sixths, negative 1 third, and then 11 sixths. Then plus, right, plus this vector here, right, there's the row space vector, plus the null space vector. But remember, if I got I'm going to have this as the row space vector plus the null space vector, and then I got another, null space vector over here. So, putting them together, I'll just have plus any null space vector. So the row space vector plus, and then some multiple. Again, I'll use a different letter this time. Say again s times the vector 1, 2, negative 1, 2, 1. So again, this is belonging to the row space of A, and any one of these vectors belongs to the null space of A. Right. And again, s is just any scalar, any real number here. And you can test it out. Replace s with any number you want and find a sum, and you'll see that you get a solution to this equation up here, right, this ax equals b. You'll see that working out. And I'm not going to do that here, but you can test it out yourself. Plug in any value for s you wish, add them up, and you'll get something that satisfies this equation. All right, so I got one more example doing the same thing. But this time, the projection onto the null space might be a little more difficult, because so far every null space I've shown you has had a dimension of 1. And so we could consider a basis for it orthogonal. Alright, so this time I got a 3 by 4 matrix A and matrix a B there. So our vector x, I'm not going to write out the equation this time. Our vector x, this is a 3 by 4. So x is going to have 4 components, right? The variable column vector, right? So a 3 by 4 times a 4 by 1 will be a 3 by 1, right? 3 by 4 times a 4 by 1 will be a 3 by 1. Alright, so I'm going to make my augmented matrix and put it into reduced echelon form, reduced row echelon form. Alright, so I'm going to just pause the video and just kind of put this in and get to the reduced echelon form and come right back to you. Okay, so I've gone to the matrix, I've gone to the calculator, put in the matrix, this 3 by 5 matrix, put it in reduced row echelon form, and got this following result. Okay, so I look for my pivots, right, the leading ones in these rows. So x1 and x2 are my leading variables, my basic variables. This time there are 2 non-pivot columns that correspond to variables. So there are two free variables, x3 and x4. So this time the null space of matrix A is going to have dimension 2. Right, these are free. And as I like to do, I'll call x3, say, S, and I'll call x4 T, where S and T are any real number I want, right? Just replace them with some parameter. Alright, then from the first equation, we're getting that x1 would be equal to 5, and then plus 2s, right, plus 2x3, and then minus t, minus x4, right? So 5 plus 2s minus t. And from the second equation, we're seeing that x2 would be equal to negative 7, then minus s, and then plus 3t. Alright, and then we put this all together, and we can write our general solution. Right. So the general solution to this, to ax equals b, so the general solution to a times x equals b will be the following. X equals, now I'm going to, I've got x1, x2, x3, x4 listed here. Again, these are going to be vectors from R4, so I'm not going to be able to picture it this time, show you like a website, or a picture, it's R4. But the stuff without the free variables would be 5, negative 7, 0, 0. Right, the vector 5, negative 7, 0, 0. So there's the a particular solution to the system. Plus, and then looking at the s's, I'll pull s out. And then the coefficients of s going down, the components are 2, negative 1, 1, 0. Plus, and then the stuff with t, right, the terms with t in it, going down the components, have t times the vector negative 1, 3, 0, 1. Right. So again, this is a particular solution, say xp, right? Just one particular solution to the system. And then the vectors attached to the free variables give you the solutions, describe all the solutions to the corresponding homogeneous, that was x sub h, right? Or just, they describe every vector that's in the null space of A. Alright, so we have the null space of A. Right, the null space of A is the span of these two vectors, right? The span of the vectors 2, negative 1, 1, 0, and the vector negative 1, 3, 0, 1. And then we can look back as well at the reduced echelon form, right, which was right here, the reduced echelon form of my matrix A, and get the row space. And you'll see that they are orthogonal complements. The row space would be the span of, there were two pivot rows here in reduced echelon form. First row, again, I'm going to write them as columns, right? 1, 0, negative 2, 1. And the second pivot row there, 0, 1, 1, negative 3. Right, and you can double check that these are indeed orthogonal subspaces. Take the dot product of this vector and this vector, this vector and this vector, this vector and this vector, this vector and this vector. There'd be 4 pairs I'd need to check. But if you took the dot product of all 4 pairs of these basis vectors, you'll see that they're all the dot products are 0. And all 4 of these together make a basis, would make a basis for R4. Right? So R4 would be the direct sum of the row space of A plus the column, the null space. I said column, I was writing column, plus the null space of A. Right, remember the row space of a matrix and the null space of a matrix are orthogonal complements. Alright, so this means, again, I could take any vector from R4. I should be able to take any vector from R4 write it as a vector from the row space plus some vector from the null space, xr plus xn. All right, and what I'm going to do, is do that with this particular solution like I've been with the last couple of examples. Because notice, this would not be in the row space. Right? Look at the row space. The row space is made up of all linear combinations of these two. If I wanted to make 5, negative 7, 0, 0, I'd have to have 5 of this first one, negative 7 of the second one, right? Because those are the only ones that have components that are non-zero in the first and second slots. If I took 5 of this first vector and negative 7 of the second vector, I'd get 5, negative 7, sure, but then I wouldn't have 0 and 0 as the second and third component. So this is not in the row space of A, right? This is not in the row space. All right, and then additionally, it's not in the null space, right? Because I'd have to take none of this and none of that to get 0 and 0 in the second component, third and fourth components. So here's a vector that's not in neither the row space or the null space. So what I'm going to do is I'm going to break it up and I'm going to decompose it into a vector from the row space plus a vector from the null space as we had in the previous examples, right? So I'm going to write that particular solution, 5, negative 7, 0, 0. And I'll call this vector x here as some vector from the row space plus some vector from the null space, right? The sum of two orthogonal vectors, do the orthogonal decomposition. All right, well, just to stay consistent here, again, you could project this vector onto the row space and then subtract it to get the projection onto the null space, or vice versa. Just to stay consistent, I'm going to project this vector onto the null space. We'll find xn again. All right. So I'm going to project x. I'm going to project, again, I called it x here, onto the null space of A. All right. Well, the last two examples, the null space of A had a basis with a single vector. All right. So I could just say it was an orthogonal basis, right? Vacuously. This basis, however, right? So again, I'm trying to, if I want to project onto a subspace, I need to find an orthogonal basis for that subspace. Key being orthogonal for the null space of A. So I have a basis here, right? A basis for the null space is this set with the vector, 2, negative 1, 1, 0, and the vector negative 1, 3, 0, 1. And the question is this an orthogonal basis for the null space? I'll take their dot product. That'd be negative 2 minus 3 is negative 5 plus 0 plus 0. The dot product is negative 5, not 0. So this is not an orthogonal basis. So, and I did this in, I think, my last video. If you're trying to project onto a subspace and you don't have you have a basis for that subspace that's not orthogonal, you can use that basis to construct an orthogonal basis for that subspace by using the Graham-Schmidt process. All right, so I'm going to do that here. So I'm going to call these vectors from my basis, my original basis. I'm going to call these vectors v1 and v2, just so I don't keep writing them. Right. There's v1 and v2 from the original basis. And the Graham-Schmidt process is, I'm trying to construct orthogonal basis say with vectors u1 and u2. Alright, well, the first step is simple. For u1, I just let it be v1. Just pick the first vector in my original basis. Right. And I'm hoping you've seen this procedure before, right? This Graham-Schmidt process. Right, so u1, easy, just gonna let that be v1. So the first vector in my orthogonal basis will be 2, -1, 1, 0. Then the second vector in the orthogonal basis, u2, will be the second vector in my original basis, but then minus its projection onto the first vector in the orthogonal basis. So minus all of its projections. Now there's only one vector previously, so the projection of vector 2, v2 onto u1. And that's it, right? And there's no other, there weren't any other vectors before this to project onto. Alright, so v2, that's -1, 3, 0, 1, minus, and the projection, right, we're projecting v2 onto u1. So we're projecting -1, 3, 0, 1 onto 2, -1, 1, 0. So remember, the numerator of the scalar of the projection vector was the dot product of these two, right? The inner product, but here the inner product is the dot product. So what's the dot product of these two vectors? That'd be -2. I already said it was -5, right? -5. So -5 in the numerator divided by, and then the inner product of u1 with itself, right? The vector you're projecting onto with itself. So 2, -1, 1, 0 with itself. That'd be 4 plus 1 plus 1 plus 0. Be 6. So -5/6 times u1, right? Times 2, -1, 1, 0. Alright, so this gives me a new vector. Right? So I'd have -1. Now this is, remember, plus 5/6 times 2. I'll just write it out. -1, 3, 0, 1. And this is positive 5/6 times that, so we have plus, and then 5/6 times 2 would be 5/3. Then positive 5/6 times -1 would be -5/6. Then positive 5/6 times 1 would be positive 5/6, and then we have 0. Alright, and then putting these together gives me the second vector in my orthogonal basis. Alright. So this is -3/3 plus 5/3, be positive 2/3. And this is 18/6 plus -5/6 will be 13/6. Then 0 plus 5/6 is 5/6. Then 1 plus 0, 1. Alright, and if you'd like, I can pull like a sixth out of this. This would be 1/6. Times 4, 13, 5, and 6, whatever. Right. So these vectors, 2, -1, 1, 0, and this 2/3, 13/6, 5/6, and 1 form an orthogonal basis for the null space. And you can double check that by taking their dot products and seeing that they are orthogonal now. And they are linear combinations of these two vectors from the original basis for the null space, so they belong. Right. Yeah. Okay. So now I want to project. Let me write that out. Let me write out the. So now I have an orthogonal basis for the null space of A. And it's this basis here with, again, the vectors 2, -1, 1, 0, and 2/3, 13/6, 5/6, and 1. Right. Or 1/6 times that if you want. All right. And I'll call these vectors u1 and u2 as I did before. Right. Vector u1, vector u2. And we're projecting x, right? X was the vector 5, -7, 0, 0. We're projecting it onto the null space, right? So that was xn. So remember, the projection of a vector onto a subspace was the sum of the projections onto each vector in the orthogonal basis. So it's going to be the projection of x onto u1 plus the projection of x onto u2. Alright, so this first one, the projection of a vector, I did projection earlier, right? Remember the numerator is the dot product of these two, the inner product, which is the dot product, so 10 plus 7, right? So 17 for the numerator. And then the dot product of this with itself was 6, right? u1 with itself is 6, 4 plus 1 plus 1, times vector u1, right? So times 2, negative 1, 1, 0, plus, and then the projection of this vector onto u2, okay, is, again, I'm just doing the first two components really, right? The dot product of this with itself, of 5 negative 7, 0, 0 with u2, doing a 10 thirds, right? 5 times 2 thirds is 10 thirds, then negative 7 times 13 sixths would be negative 91 sixths. So 10 thirds, which is 26 minus 91 sixths, would be negative 71 sixths. Yeah, 10 thirds, 26 minus 91 sixths. Yeah, negative 71 sixths for the numerator, divided by, and then, the dot product of u2 with itself. Alright, so I'm going to actually pause this and do some calculations out and get the final result. Alright. Okay, so after doing this was the dot product of x with u2 divided by the dot product of u2 with itself times u2. Went through and did all these calculations off on some side sheet and got, this should just be simple. It's arithmetic, there's a lot of fractions involved. So the projection of our particular solution onto the null space is this vector 185 over 41, negative 270 41sts, 57 41st, negative 71 41sts. Alright, and now I'm going to find that xr. Right, I'm just going to subtract this from x, and we'll get our vector from the row space of A. Right, so remember that our xr, the vector from the row space, is just our vector, our solution x, or our solution 5, negative 7, 0, 0, minus xn. Alright, so again, I'm going to pause it for a second and do these calculations pretty quickly. Okay, so after subtracting xn from x, I'm getting the vector xr, right, the vector from the row space, 20 41sts, negative 17 41sts, negative 57 41sts, and 71 41sts. And you can verify that this is actually a solution of ax equals b from way back in the beginning of the problem. So I have my x, 5, negative 7, 0, 0, broken up into a vector from the row space plus a vector from the column space. I keep saying column space. Sorry. I have my solution x broken up into a vector from the row space plus a vector from the null space of A. Right, the row space and null space are orthogonal complements. And if you'd like, you can actually double check that the dot product of these two is 0. Right, and you can again go ahead and verify that for yourself. Alright, and finally, after all this, we can use this and rewrite our general solution to this system again. Right, so going way back now, before all the Graham-Schmidt stuff, remember our general solution to ax equals b, right, where a was this matrix and b was 5, 8, negative 9. Our general solution to ax equals b looked like this, with 5, negative 7, 0, 0, plus some multiple of 2, negative 1, 1, 0, plus another multiple, some multiple of negative 1, 3, 0, 1, right? So, some vector from the null space. All right, so I can express now the general solution in another way, right? Like this, where I can express x as a vector from the row space of A, which was this. I'll write it with the fraction outside where every single one of them was 1/41. So 1/41 times the vector 20, negative 17, negative 57, and 71, plus, right, plus, and then this second vector, I don't need to write this again, because this vector here is from the null space, and all of these vectors are from the null space. So when I write this as this vector plus this vector here is just some multiple of 2, negative 110, and negative 1301. So I'm just going to write this again. Plus s, some multiple of 2, negative 110, plus t times, negative 1301. Right. And here you go. There's a general solution. Just another way to describe the general solution to this system, ax equals b, where now I have a vector from the row space, right, this 1/41 times this crazy vector here, plus, and then when I pick a value for s and t, I get some vector from the null space. Right, so one vector plus some orthogonal vector to give me any solution to the system I wish. Right, and again, s, I guess I should write out that s and t are any real number I want. Right. Okay, and you can verify that. I know there's lots of crazy fractions here. I use the calculator a lot, but you can verify this. Pick any value for s and t that you want. Pick 100 for s, negative 5 for t, a third for s, 15 for t, whatever you want. Plug them in, get some solution, and you'll see that it's a solution. You can plug in the vector to ax equals b and see that it's actually true. Right? You might have to use a calculator to verify that stuff. But yeah, but this is all coming from, these are all consequences of the fundamental theorem of linear algebra, that for any matrix, the row space of the matrix and the null space are orthogonal complements. Right? So therefore the row space of A transpose and the null space of A transpose would also be orthogonal complements, right? So therefore the column space and left null space of A would be orthogonal complements as well. But the key here, I think the one I want you to remember the most, is that the row space of a matrix and the null space of a matrix are going to be orthogonal complements. And if it's an m by n matrix, that would mean that Rn can be expressed as a direct sum of the row space and null space of the matrix. So you can take any vector from Rn, write it as a vector from the row space plus a vector from the null space, as we have done in the past 3 examples. I know they took a while, but sometimes they do take a while, especially if we need to do the Gram-Schmidt process to find an orthogonal basis for the null space or the row space. It depends on which one you want to project onto. Right? Do you want to find that xr or that xn first? And whatever space you're projecting onto, you first need to find an orthogonal basis for that space to make the projection easier to find, easier to take. All right, so lots of stuff here. Right? Really not a lot to remember, just a lot to do. Right? The only thing to remember is that fundamental theorem, and how you can express a Euclidean space as a direct sum of a row space and a null space of a matrix. That's not a lot to remember, but there is a lot to do in problems involving them, where you're asked to express solutions as a row space vector plus a null space vector. Alright, so again, hope you enjoy practicing problems like this. Hopefully this wasn't too crazy. I know this last example had a lot of stuff in it, a lot of fractions and a lot of projections. Hopefully it was reasonably easy to follow, and hope you get good at it, practicing it on your own a lot more. That's the only way to get better at anything. Alright, and thank you very much for watching.